presented by Suryadipta Majumdar from Concordia University. He'll be telling us about their system TenantGuard, which offers scalable runtime verification for VM-level network isolation.
Thanks for the intro. Hello, everyone. Today I'm going to talk about TenantGuard, which is a research collaboration between Concordia University and Ericsson Security Research Canada. And I have one of my co-authors, Yosr Jarraya from Ericsson here. So let's start with the highlights of this paper. So here we present a TenantGuard, a VM-level network isolation verification system. So TenantGuard can verify pairwise reachability for over 25,000 VMs within 13 seconds, so which is significantly faster than the existing approaches. And our approach is built on OpenStack, which is one of the most popular cloud platforms these days. And the approach is based on a hierarchical model for virtual networks. And in this work, we leverage efficient data structures, incremental verification, and parallel computation. So let's start with the problem. So isolation breach is one of the biggest security concerns in cloud, or more specifically from the cloud tenant's perspective, right? So multi-tenancy is a basic nature of cloud, which allows business rivals to use the same cloud service. Just for an example, if Democrats and Republicans are using the same cloud, and very possibly something may go wrong, and to be politically and technically correct, any of them can get hacked, right? And then in this case, we actually don't need any help of other country because these cloud platforms have enough implementation flaws which allow you to breach isolation. So just for an example, here I put some OpenStack real-world vulnerabilities, which so one of them allows a tenant to create router ports into other tenants, and the other vulnerability says that security group rules are not effective on instances immediately. So even if you add security groups, they are not being effective. So there are many more in the provided link. So to identify the network isolation, or more specifically virtual network isolation, is very important, and one possible solution could be virtual network isolation verification in the cloud. However, verifying virtual network is not so trivial because there exist different challenges. So most importantly, the size of virtual networks. So in this particular case, we are talking about more than 150 million VM pairs. Also, we have diverse and distributed network functions, such as layer 3, layer 4 routing, NATing, firewalling. Additionally, for verification, we need to collect large amount of data from different sources in the cloud. And finally, because of the self-service nature of cloud, tenants are allowed to create, delete VMs, subnets, routing rules, security groups, very often. So as a result, these verification results may get invalidated very quickly. So if a verification approach responding in minutes or hours, that might not be sufficient. So to this end, we have categorized the existing approaches into three types. The first one is designed for physical networks, so hence they're not so suitable for virtual network environments. The second category is focused more on small to medium virtual infrastructures, so that they're not so designed for millions of VM pairs. And the last category can support VM level reachability. However, they take minutes to hours for over 100 million VM pairs. So before jumping into the solution, let's just talk about the assumptions. In TenantGuard, we have three major players. cloud tenants, cloud providers, and TenantGuard. So cloud tenants provide verification requests or security properties to TenantGuard, and cloud provider providing the input data or the cloud data to TenantGuard. And in this work, we focus more on verifying security properties defined by the cloud tenants. And we are not detecting any specific attacks here. And in this work, we rely on the correctness of input data, also existing solution at other layers such as virtual layer 2 or physical layer. And also, we assume that there is no sensitive information leakage from the verification results as we are dealing with reachability. So here, this is a very high-level architecture of TenantGuard. And in this talk, I mainly focus on the box in the middle, which contains different components and steps of TenantGuard. So let's start with the key ideas of TenantGuards. So at first, we devise a hierarchical model of virtual network. So we identify different components of virtual network and their interconnections so that we can formularize this problem of reachability. And then in the next step, we propose a top-down verification approach where we start with the prefix level isolation verification and then selectively go down to IP level verification, or in other words, VM level isolation verification. And to implement the top-down verification, we get aid of efficient data structures such as radix trie and XPath binary trie, because they provide very efficient searching and insertion operations. So now let's talk about each of them into more detailed manner. So in our hierarchical model, we identified different components of a virtual network, starting from external network, router gateways, routers, subnets, VMs, and so on. Also, we have identified different access control points or routing rules points in this model, so that when we want to check reachability in between two VMs, then we know where to check and what to check. So we know where are the routing rules, NAT rules, and security groups. So I'm just going back to the problem we're trying to solve. So we wanted to verify VM pair-wise reachability. And once we have the model, we have formularized the problem. Now, a naive approach would be to check all possible VM pairs and answer, right? But here we are talking about over 150 million VM pairs, and the response time would be significant and might not be very meaningful. So we propose here the top-down verification approach, which contains three major steps. In our first step, we check prefix level isolation between subnets within the same tenant environment. And then in our second step, we check again prefix level isolation, but the subnets belongs to different tenants. And from these two steps, we identify the subnets which are not reachable. And we, for the third step, we eliminate all those subnets which are not reachable, so that at the VM level isolation verification, we can significantly reduce the space and improve the response time. So at the step 3, at VM level isolation verification, we only check for those subnets who found to be reachable. Now, to implement this work, we use two main data structures. Firstly, radix trie. So what we are doing here is we are transforming the routing tables rules into radix tries. So radix tries contain zeros and ones. So at a particular position, we have a series of zeros and ones, which will match with a IP prefix, and at that node, we store the next hop. So in cases we don't have any matching rule, we don't store anything, or we store null, right? So once we have populated this radix trie, then when we want to match with a destination IP prefix, at first we run longest prefix match. And once we get the matching rule, we want to go further because we now have a destination IP prefix. There might be multiple routing rules which might match with this prefix. So we further perform pre-order traversal, which check the subtrie under that prefix match and try to identify whether that destination IP prefix will match with multiple rules. So if multiple rules match, then we split that destination IP prefix into multiple IP ranges. Once we have these IP ranges, then we store the results of matching routing rules into an XFAS binary trie. So again, we are using this XFAS binary trie because of its efficiency in searching and insertion. And the leaves of XFAS binary trie stores different values for the verification process. For an example, we have lower and higher bound of IP range. We also store the verification status, whether there is a loop or black hole or reachability, or it's still on process. And also we store a tuples containing all the visited nodes, including the next hops. And we iteratively populate this XFAS binary trie till we cover all the hops. So this is just a simple step. So we will iteratively repeat this step to populate this XFAS binary trie and to get all the possible ranges till we cover all the hops or all the rules in the routing table. So this is basically our top-down verification approach. However, as I mentioned that for the dynamic nature or self-service nature of the cloud, the verification results might go invalidated very quickly. And to redo the verification is expensive and somewhat unnecessary. So we propose an incremental verification approach. Where for an example, if we have a new security group, so security groups are added at the VM level. So we don't repeat all the steps. We just update the radix trie for that security group and then run security group verification. So in that way, we escape multiple steps in the verification process and hence reduce the overhead of incremental approach. So our solution, TenantGuard, is built on OpenStack. So we used OpenStack version Kilo with 1 controller and 80 compute nodes. For parallelization, we used Apache Ignite. And we have also integrated our solution with OpenStack Congress, which is a policy verification engine, so that tenants are allowed to run more specific queries through the TenantGuard output. Then we evaluate the performance of TenantGuard, where we found that the data collection and processing steps take around 1.5 to 2 seconds. So as this is a one-time effort, it seems quite reasonable. And on the right side, we compare our efficient prefix-to-prefix approach with baseline algorithm and also closest state-of-the-art work NOD. And it shows that TenantGuard performs 82% faster than the baseline. But still, if you look at carefully, you'll see TenantGuard requires more than a minute to verify the largest data. So to further improve the performance, we instantiated up to 16 worker nodes in Amazon EC2 and distribute the task of TenantGuard in parallel. And then TenantGuard can verify reachability for over 160 million VM pairs in 13 seconds. In our experiments, we also measured the relationship between cluster size and speed up gain to show that it's not always beneficial to just distribute the task because of the communication overhead. And at the last part of our experiment, we vary different factors and try to see the effect on TenantGuard on them. So number of VMs and hops have very less effects due to the reduced complexity and design. So the more detailed description is provided in the paper. Also, the number of routing rules has almost no effect because we are using the radix and XFAST binary trie. So in conclusion, to address the limitations of some of the limitations of TenantGuard, we intend to integrate TenantGuard with other existing solutions for other layers, such as physical layer or layer 2, to provide end-to-end isolation guarantee. Also, we want to explore how we can ensure integrity of input data, and also to address privacy issues from the verification results. So in summary, here we propose TenantGuard, a VM-level network isolation verification system. It is built on OpenStack, and TenantGuard can verify reachability for over 150 million VM pairs in 13 seconds. Thank you very much.